Okay, so here we're going to go over the transformations of a function in function notation. Now, you have covered these transformations before. You started covering these transformations, I believe, as early as grade 10. You started using the correct terminology in grade 11, so much of this should be review, but if some of it's not, that's okay too. We're going to go pretty slowly through it. I have already filled in the types of transformations that we have. Now you'll notice each of these transformations comes from one of the values inside our equation here. So for instance, our A value will tell us our vertical stretch or compression factor, and it will tell us whether or not there is a vertical reflection, and that's a reflection over the x-axis. Okay, our K value here in blue will tell us our horizontal stretch or compression factor. Although it will not be equal to K, it will tell us the horizontal stretch or compression factor, and it will tell us whether or not there is a horizontal reflection, and that would be over the y-axis. Our P value here would tell us our horizontal translation, and our Q value tells us about our vertical translation. Now you'll notice there are 6 different types of transformations here. 3 of them are vertical. 3 of them are horizontal. Okay, now each of these, so vertically we can transform a function by stretching it, compressing it, translating it, or reflecting it, right? Now we can make all of those transformations horizontally as well. It will, the location of our values inside our function notation will tell us what kind of a transformation we're working with. So we're going to move forward. We'll take a look at these and we'll see exactly how we can put them to use. Now, we can use a mapping rule to help us particularly graph a function from its transformations. In particular, in actuality, when we're doing that, we're taking these values, A, K, P, and Q, that tell us about all of our transformations, and we put those values into a mapping rule in order to plot transformations point by point. Now, when you're doing so, when you are writing out a mapping rule, you must write out x, y, in brackets, like an ordered pair, because that's what it is, becomes, so it transforms. So this original xy, that's from our base function. That's not transformed. And then our transformed points would be x over k plus p, a times y plus q. Now we will see how that works as we move forward, but when we build up our mapping rule, you'll notice, that the 2 values that are working with x here, that are manipulating x, are K and P. K and P are the 2 letters from up above. I'm sorry, my zoom is a little wonky here. Are the 2 letters from up above that are inside our function, right? So we have f at and then K times x minus P. All of this here is inside my function. And so those affect my x value. My x value is my domain. Those affect my x value. Those affect horizontal transformation. So that is the horizontal stretch or compression, the horizontal translation, and the horizontal reflection. Okay, on the outside of my function, notation, I have A and Q. A and Q will affect my vertical stretch or compression, my vertical translation, and my vertical reflection. Now, when I say on the outside, that means A is multiplying times F. Right? A times F here, and F is evaluated at K times x minus P, but A is multiplying times F, and then we're adding Q afterwards, right? So those are working on our function from the outside. Now, A and Q, you'll notice, are the 2 values affecting Y here, right? So our vertical values, our vertical transformation values, are going to affect y. That makes sense. Y is our vertical coordinate. Our horizontal values, k and p, will affect x. That makes sense. X is our horizontal coordinate. So from this equation here, this is a transformed function. This tells us our transformations. We don't know which base function we're working with. So you see our function notation here, f at negative 1/2 times x minus 1. Right, so we have a general base function. We could be applying these to any base function we wanted to. And we want to break apart which transformations are getting applied here. So let's try and we'll copy our general equation down so we can see it as we are working with it down here. Perfect. So I can see as my equation is being put together here, I see this 3 is being multiplied by the f. Well, that's the same role that the a plays. So that tells us that our a value, a equals 3. Okay, now the negative 1/2, if we compare that to the equation that's going on down here, negative 1/2, first of all, it's inside the function. Right, so it's inside our function notation, and that means the only options are k and p, and then it's multiplying times x, right? It's multiplying, in fact, here it's multiplying times x minus 1. So in that case, it's our k. K is what multiplies times x, p is what subtracts from x. So k is negative 1/2 up here. K equals negative 1/2. And then we have our p value, x minus 1 here, x minus p. So p equals positive 1, right? Because it's being subtracted from x. Positive 1 is being subtracted. So p equals 1. And then on the outside, I see a q value, and that is q equals positive 4. I can see that's at the end. They're in the same position, and they're doing the same thing. The position matters less than what they're doing. In this case, it's adding onto every other thing in there, right? That's what plus 4 is doing over here. So q equals 4. Now, what we're working with here, because a equals 3, we have a vertical stretch or compression, we might not be sure yet, by a factor of, and then we can double check what we were working on up here, vertical stretch or compression by a factor of the absolute value of a. So we can take the absolute value of a, that's by a factor of the absolute value of 3, which equals 3. So it's by a factor of 3. Now, since 3 is a number that's greater than 1, then when 3 multiplies by this function, when 3 multiplies by it, then it's going to create a bigger value, right? Anything multiplied by 3 is bigger than what we began with. So since it's a bigger value, then it's a vertical stretch. If this was by a factor of something in between 0 and 1, then it would be a compression. Okay, because then if we multiply something by a value in between 0 and 1, then it gets smaller. And if it gets smaller, then we're compressing our values. Now, we can go on into our k value. So k, it's a horizontal something. It's either a stretch or compression by a factor of, and here, if I double check what's going on up top, our compression factor, our stretch or compression factor is by a factor of 1 over the absolute value of k. So it's by a factor of 1 over k. And there we are, 1 over k. Now k equals negative 1/2. So that's 1 over negative 1 over 2, the absolute value of that. And that equals, that's the reciprocal of 1 over 2. Sorry, this reciprocal of 1 over 2, which equals 2. So it's by a factor of 2. By a factor of 2, since it's by a factor of 2, that's a number greater than 1, so it's a stretch, not a compression. Now, we do notice as well here, since k is less than, since k here is less than 0, right? It's a negative value that we're working with. Oops. K is a negative value that we're working with. So we also have here a horizontal reflection. If it's a horizontal reflection, then what we're working with here, let's give ourselves a little bit more space. And we'll call that 3. A horizontal reflection. Horizontal, I'll put that in brackets. Not everyone talks about it as horizontal, but it's a reflection over the y-axis. Good, now since p equals 1, we have a translation 1 unit, and since p is positive, then it's 1 unit right. Okay, and then our Q value, Q equals 4. It equals a positive 4. This is a vertical translation. This is a vertical translation 4 units up. Okay, we must specify the direction of our translation if we have a translation that we're working with here. Let's see. Now we can use these values, right? We've found the values of A, K, P, and Q. We can use these values to substitute in to our, we don't need this anymore. We can substitute these values into our mapping rule. Okay, so A equals 3, K equals -1/2, P equals 1, Q equals 4. Let's try and build it right here. So that means when I'm working, I have X over K. That means that's X over -1/2. All right, so X divided by -1/2 plus P. Plus P is 1, so plus 1. And then I'm working with A times Y, right? A times Y, and that equals 3 times Y plus Q. Well, Q equals 4, so 3 times Y plus 4. Now, the way these transformations are working down here is this means that my X value, whatever my original X value was, now it's going to be divided by -1/2, and then we'll add plus 1, and that will give us our new transformed point, the X value of that. So what I'm working in here, if I simplify this a little bit further, X divided by -1/2, that equals -2X, and then plus 1 from my P value here, and 3Y plus 4. There we are, it's simplified for us. Now we can substitute in a point that was on our base function in order to find the new transformed point, right? So if our point 2, 3 was on the base function y equals f of x, we can find the transformed coordinates by substituting these values into our mapping rule up above. So that is, we begin with the point 2, 3, and that transforms to -2 times x. In this case, -x is 2. Plus 1. And then 3 times y, in this case my y value is +3, so 3 times 3 plus 4. And that means that my new transformed point will be -2 times 2, that's -4, plus 1, that's -3. And the y coordinate will be 3 times 3, that's 9, plus 4, that's 13. So -3, 13 will be my new transformed point. Now, sometimes we're working with a function with the transformations in this form. Other times we're working in a similar form, but we're given the base function. So let's try something out like that. Let's, sorry, I'm carrying this around with me until I need it again. I think we'll need it here. So we're working, here we know the base function. Well, we're given a base function. We need to find out which one it is. And that's why this does not have an f in it, right? There's no f. There's no f at x, no f at anything involved here. But what we do have is we have another something that's going on, and that is the radical, right? If you notice the radical here, that's our square root function. So our base function is y equals the square root of x. Okay, it's nice and simple here. If you're confused a little bit about base functions, then double check our note from 1.3 last time. Okay, so we know our base function. Our base function is y equals the square root of x, or if you'd rather, we can say g of x equals the square root of x, or we could just write out the word the radical because it's a radical function, either would be fine here. Now, if we're listing the transformations going on here, what we need to find first are our values. We need to find a, k, p, and q. Okay, the problem is, here we do not have f at x that we're working with, so they're going to be in slightly different positions. But we can see here, right off the start, we can see that a multiplies times f at something, right? F at x. Now, in this case, there is no f at x, but we know our base function is the square root of x, so whatever's multiplying by our radical, that's going to be our a term. In this case, our a term is -3. Since it's negative, since it's less than 0, then we have here a reflection over the x-axis. Okay, so we use that, we consider it. We also have, because it's the number 3, we have a vertical, it's either a stretch or compression, by a factor of 3. By a factor of 3. We always state just positive here. our stretch or compression factor. Since 3 is a number that's greater than 1, then again we have a vertical stretch. Okay, and this is all from, and I should have copied this down beside. This is all because A equals -3. Those are the first two transformations there. Next, I have my k value. So my k value is inside my function, right? My function here is the square root of x. So that means underneath the square root where my x normally is, there's going to be my k value. My k value is multiplying times that x inside my function. So that is 2. So my k equals 2. Okay, well, if k equals 2, then I have a horizontal. It's either a stretch or compression. It's by a factor of 1 over the absolute value of k. And I get that, again, I get that from up here. 1 over the absolute value of k. That tells me my horizontal stretch or compression factor. 1 over the absolute value of k in this case equals 1 over 2. Now, since 1 over 2 is less than 1, it's in between 0 and 1, then we have a horizontal compression by a factor of 1 over 2. Next, lastly, we have my P and Q values, and here I can, if I'm getting a little bit lazy, then I can state them together. So my P value here, my P, it says x minus 3, and since I'm working with x minus P, that means P equals positive 3. And afterwards, at the end of my function here, I'm adding 4, so again, my Q value equals 4. So Q equals 4. So here I would say that I have a translation 3 units right, and I have a translation 4 units up. I don't necessarily need to specify that my translation 3 units right is a horizontal translation because I'm saying it's right. If it's going right, if I'm shifting it, if I'm translating it a certain number of units to the right, I know it's horizontally moving. And if I'm translating it 4 units up, I don't need to specify that it's a vertical translation because I state the direction. You would not get full marks here if you don't state the direction of your transformations here. Now, we can find our new points by, whoops, I'm a little bit ahead of myself there. That should have been gone. I can find my new points from my transform points that will be on this function by finding some points that would be on the base function, my radical function here, and then transforming those. So finding some common points on this base function. I know the point 0, 0 is on this base function. How do I know that? Well, my equation is y equals the square root of x. And I can substitute in any value for x here and see what my y value becomes to come up with some points, right? So I can sub x equals 0 into this, and I'm left with y equals the square root of 0. That means y equals 0. So that means that the point 0 from here, 0 from here is on my base function. Next, I can try, if I want to, if I'm not really sure where this is going, I can try the point -1. So if I try substituting in sub x equals -1, then I can see that y equals the square root of -1. If I put that into my calculator, I find that it says error. And that's because I cannot take the square root of a negative number, so I don't get any point. There's no point from here. Right, and if you're familiar with the domain of your radical function, then you would know we cannot substitute in negative values for x. But anyways, we can keep right on going. We can sub in x equals +1. That gives us from y equals the square root of 1. That gives us the point 1, 1. And pushing forward, we can keep right on going. We can try substituting in the point x equals, and we want to try and think of points that we can take the square root of without a calculator, right? We should be able to handle all of this without a calculator. So the square root here, let's try 4. I know the square root of 4, so if I sub in x equals 4, then I'm working with y equals the square root of 4, and that means y equals 2. So then the point 4, 2 will be on my function. And I can keep going using that same strategy. So I have the point 0, 0, I have the point 1, 1, I have the point, 4, 2. I have the point 9, 3, etc. Now these points, I have actually already gone ahead and plotted these 4 points, 3 of these points here. The 4th point wouldn't quite fit, it would be right around here on here. Now this base function, if I'm ever sketching more than one function on the same graph here, then I need to make sure I'm labeling it. So you'll notice I've labeled it here. Now I can use our mapping rule to graph this transformed function. I can come up with the mapping rule from these values here, right? So my mapping rule, x and y become x over k, so that is x over, in this case, k equals 2, so x over 2 plus p, so that is plus 3, and my y coordinate becomes a, and that is negative 3 times y plus q, that's plus 4. So I can substitute in these values into my mapping rule to come up with new points. So I want you to try that out the exact same way we tried it here. I want you to pause the video if you're going along for the first time. I want you to pause the video, see if you can substitute these in on your own. But otherwise, we are going to substitute in at least one of them here. So let's try substituting in the point 0, 0. So 0, 0 becomes 0 divided by 2 plus 3. And negative 3 times 0 plus 4, where I have substituted in x equals 0 and y equals 0 into my mapping rule. I push forward, and I'm working with here 0 plus 3. That is the point. The x coordinate is at 3, and my y coordinate, negative 3 times 0 plus 4, is at 4. So then I can plot the point 3, 4 here, 3 across, 4 up. Here's my first point on my transformed function. And we could see, I want you to transform the rest of that. You should end up with something that, that looks a little bit like that in general. I want you to transform the rest of these 3 points here. Now from there, you'll notice this example, we really broke down for you the steps involved in plotting a transformed function, right? First, you state the base function. Then you list the transformations, and perhaps it would be helpful here to say this. First, we state the base function. State base function. Then we we find a, k, p, and q. And then we state the transformations. Now this step here, you don't necessarily have to do every time if they don't ask you to state the transformations, but it often can help you visualize what's going on. You always need to do this, is you need to find common points. And by common, we mean easy to calculate points without a calculator. Find common points on the base function, right? Base function. And 5, you create your mapping rule. And then 6, what we did is we used our mapping rule on these common points. Now, you should be able to follow these 6 steps to handle graphing another one here. You can try it out. The solution will be posted online afterwards. And actually, you know what? In this particular case, you can check your own work into Desmos. You can check with Desmos here. Pushing forward. Now here, I really wanted to make sure we went over example 3 with you. And I'm sorry, I already had some of the work finished here. We want to make sure we go over example 3 here, because not always will we have A, K, P, and Q easy to find, right? Sometimes we need to do a little bit of work manipulating our equation before we find those. So let's go on ahead. I know I was carrying it with us and I lost it. There it is. Let's bring this down with us here. Good stuff. So what we will notice in here, you might be tempted to say, okay, I've done this a couple times now. I can see that A is multiplying times my my base function. I can see that my base function is y equals 2 to the power of x. Maybe you can see that already. Then you can say, okay, well, I see my a here, that's -6. I see my k, that's a 4. That's multiplying by the x. My p is -5, and my q is +3. And you would be, you'd be very close, but not quite correct in there. So we need to be very careful. What's going on right here, inside my function, is I have k times x minus p, and that's also what I have down here, k times x minus p. But when I'm working in function notation with my transformations, then I have a bracket keeping x and p together. And that means what's going on is k is actually multiplying times x and k is multiplying times p. Okay, so we need to make sure, if we're going to take our values a, k, p, and q, we need to make sure that they're set up in the same way. And that means we need to make sure that k is factored out of x and p, right? It's on the outside of some brackets here with x and p. So down here we'll notice k is not yet factored out. So this should read -6 times 2 times 4, and we can factor it out. So we put our brackets here. X minus, and since 4 is being factored out, x minus 5 over 4 in brackets plus 3. So that means that what we're working with here is an a value of -6, a k value of 4, a p value of 5 over 4, and a q value of 3. Okay, now from these values, you should be able to come up with all of our transformations. So I would like you to try that out. I'm not going to go over them in this video because we've done that a few times now. We have our letters, we have our values, our a, k, p, and q values. We have them. We can come up with our transformations. Next, though, they're asking you to practice the exact same skill. So try and make sure what you're doing is you're factoring out k first, or you're making sure that k is factored out before you state your a, k, p, and q values. Again, I will post the completed note on the Brightspace Classroom so you can compare your own work into here, but I'm not going to do that in the video. Okay, lastly, I did put in a little bit of a bonus here, and this is to help you practice. If there are any of the skills that we've gone over during the last lesson that you're still struggling with, then you can practice. You can find the domain and range for the functions on this page. You can find the intervals of increase and decrease for the functions on this page, and you can try stating the end behaviors for the functions on this page. If you're not, if you are practicing any of these, again, I will state the answers. I will show the answers in the completed note that I post on the classroom. But now from this practice, you should be able to handle the practice work for section 1.4, and you should be feeling quite a bit more comfortable with vertical stretches, horizontal stretches, and compressions, horizontal and vertical translations, as well as reflections at this point. Now, we did not necessarily go over in this video what those look like. We did cover that in class, what you can expect those to look like on a graph, and we can practice that in class more as well.